What if I told you one of the greatest mathematicians in history never really studied mathematics? I'm Saba. Welcome to Hidden Math.
Today, I want to talk about a mathematical genius named Srinivasa Ramanujan, who still amazes mathematicians to this day. He was born in 1887 in the state of Madras, which is now known as Tamil Nadu, in southern India. Ramanujan fell in love with mathematics at the age of 11, and when he was just 16, he completed his mathematical education by studying with two university students who were staying in his house at the time. During this period, he worked extensively with a book titled A Synopsis of Elementary Results in Pure and Applied Mathematics by G.S. Carr. This book was essentially a study guide summarizing existing monographs, and at the time it was considered a fairly comprehensive mathematics reference. It contained around 5,000 mathematical theorems. Ramanujan studied this book obsessively. Today, this book is often described as the book that awakened a genius, because it was after reading it that Ramanujan's extraordinary talent emerged. Ramanujan would spend hours at the blackboard, deriving his own original formulas, and he would only copy his most important results into his notebook, because he was extremely poor and could not afford much paper. As a simple example, he showed that if a plus b plus 3 are 0, then the same relationship also holds for the fourth power. Another example of the deep mathematics he discovered is an equation involving an infinite sequence of nested roots. Although Ramanujan received a scholarship from the university, he was expelled twice because he had no interest in subjects other than mathematics, such as English, history, or physiology. As a result, he began earning a living as an office clerk. But during this time, his supervising mathematicians encouraged him to share his results with prominent English mathematicians. Ramanujan first sent his work to two professors, H. F. Baker and E. W. Hobson, but they showed no interest and simply returned his manuscripts. The third professor he contacted, to whom he sent a 9-page letter that would change his life, was a famous Cambridge mathematician named G.H. Hardy. Hardy responded positively to Ramanujan's work. That 9-page letter was filled with astonishing formulas, including an infinite series involving the reciprocal of p and a continued fraction containing both p and Euler's number. When Hardy and his close colleague J.E. Littlewood examined Ramanujan's results, they were stunned and immediately convinced that Ramanujan was a true genius. Hardy later wrote that these formulas must be true, because if they were not, no one could possibly have imagined them. Hardy then invited Ramanujan to collaborate with him at University of Cambridge, and in 1914, Ramanujan traveled to England. Ramanujan's formulas had a profound impact on researchers, so much so that the Hungarian mathematician George Polya once borrowed one of Hardy's notebooks, but quickly returned it, fearing that he might become absorbed in Ramanujan's world and lose focus on his own work. Among the many areas Hardy and Ramanujan worked on were set theory, set partitions, theory of division, number theory, and divisibility theory. Although these topics are not identical when examined closely, together they form a coherent mathematical framework. Now let's talk briefly about one of the ideas that Hardy and Ramanujan developed. Students familiar with mathematics, especially those preparing for math Olympiads, are likely already familiar with partitions. So let's begin with a simple question. In how many partition ways can we write the number 7 as a sum of natural numbers? To answer this, we need a systematic strategy. For example, we can list the numbers in descending order. When we do this, we find that there are 15 such partitions. But notice, we are doing this manually, writing all 15 cases by hand. Now imagine what happens when the number becomes larger. For instance, how many partitions does the number 50 have? It becomes practically impossible to count by hand because there are 204,226 different ways. This enormous number shows why we need formulas. Partition theory provides exactly that. A way to describe these divisions mathematically. In their study of partitions, Hardy and Ramanujan made several groundbreaking discoveries. We now know that partitions connect to many different fields. They relate to sets, to numbers, to economics, such as the different ways to break down currency, and even to physics. In statistical mechanics, for example, partition functions appear in Bose-Einstein statistics. One famous result from this area is now known as the Rogers-Ramanujan identities. Partitions have fascinating properties, and this is where Rogers' mysterious and intricate formulas arise. Let's consider the partitions of the number 11. Now, suppose we impose two conditions. First, the difference between any two parts must be at least 2. Second, each partition must contain at least one of the numbers 1, 4, 6, or 9. We don't care about the specific forms, only about how many such partitions exist. What's remarkable is that under both conditions, the number of valid partitions is exactly 7. Even more interestingly, these same conditions appear naturally in the Rogers-Ramanujan identities. Now remember that this work was done around 1917, while Ramanujan was living in England, a time marked by war, hardship, and scarcity. Ramanujan suffered from long-term health problems, isolation, and severe dietary limitations. He spent long periods in nursing homes and hospitals. There is a famous story from this period. When Hardy once visited Ramanujan in the hospital, he arrived in a taxi numbered 1729 and casually remarked that it seemed like a dull number. Ramanujan immediately replied, "No, it is a very interesting number. It is the smallest number expressible as the sum of two cubes in two different ways." This story shows how deeply Ramanujan lived in the world of numbers, assigning personality and meaning to each one. In fact, Ramanujan even found a general formula for expressing numbers as sums of two cubes. Remember, we are talking about 1917. There were no computers capable of performing such calculations. In many ways, Ramanujan was truly a master of numbers. A British mathematician later remarked that all positive integers were either Ramanujan's close friends or his lovers. When Ramanujan was finally discharged from the hospital, he chose to return to India, believing the warmer climate and reunion with his family would help his health. After returning to India, Ramanujan was appointed as a university professor and became a national hero. However, his health continued to deteriorate, and he passed away at the tragically young age of 32. Ramanujan's love affair with numbers did not end with his death. Decades later, mathematicians such as Bruce Berndt published extensive work on Ramanujan's formulas. In 1976, George Andrews discovered Ramanujan's unpublished notes in the Wren Library at Cambridge. These became known as the Lost Notebooks. To this day, mathematicians continue to study these notebooks. Despite living in extreme poverty, Ramanujan taught himself mathematics, competed with Europe's greatest minds, and created formulas so deep and mysterious that they still astonish researchers today. So it makes sense that Ramanujan would inspire a story about infinity. There is a film based on his life, titled The Man Who Knew Infinity. If you're interested in learning more about Ramanujan's life and work, I highly recommend watching this movie.
Ramanujan didn't just work with numbers. He saw a world inside them. If that world fascinates you, welcome to Hidden Math. Subscribe for more stories where math hides deeper than you think.